actually finished. Okay, so if you have picked up the exam, do not discuss it in class. There's a few people who are still working on it for various reasons, unless you're one of the people who are, well actually this is being recorded so I won't say anything. And if somebody can just erase that, I would just ask somebody to erase that so it's never seen by the camera. Okay. Yes, now. Okay. Quickly. Yes, that's enough. Okay.
Whatever it may have said.
Whatever it may have said.
Maybe we can restart this.
Well, no, it'll be interesting to see how well people can actually, yeah, people can easily figure that out.
It's like the primitive version of zero and something out of
Exactly.
the computer.
Alright, so I need to check my notes for this one.
We're gonna set up the fire alarm.
Where there's smoke. Alright, so f1 of x is 1 over square root of 2 pi x squared e to the negative log squared of x over 2. And f2 of x is equal to f1 of x times the quantity 1 plus the sine of 2 pi log x. And what can you tell me about which values of x this is defined for? Just looking at this, what can we tell about which values of x is this defined for?
Positive.
Positive. Right. Both x greater than 0. These two functions turn out to be probability densities. It is not necessarily fun to prove that they're probability densities, but they both integrate to 1 and they are both non-negative. There is something else that's fascinating about these densities. Not in isolation, but only together. Does anybody remember what's interesting about these two densities? They have the same integral moments. Okay? Densities like this should not be allowed to exist. Okay? This completely destroys any chance we have of a simple theory. You would love to say, if you know the moments of a probability distribution, it uniquely specifies the probability distribution. There's lots of theorems you would love to have that are false. Right? You might remember from early in the semester the function g of x is e to the negative 1 over x squared if x does not equal 0, and 0 if x equals 0. It turns out every derivative of this function at 0 is 0. What this means is the Taylor series expansion of this function is the function that's identically 0. So in other words, Taylor series expansions are not unique. You give me your favorite Taylor series expansion, sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. That could be the Taylor series expansion for sine of x plus g of x. Or even worse, sine of x plus 1701 g of x. That has the same Taylor series expansion as sine of x. Taylor series are not unique. Unfortunately, moments suffer the same issues as Taylor series. If I know the sequence of moments of my probability distribution, that does not uniquely determine it. There are some situations where knowing information uniquely determines. If I have a discrete variable that only takes on finitely many values, okay, you give me those values, I know. You could also get it if you just know the moments. But for continuous distributions, strange things can happen. And so we need some results from complex analysis to deal with cases like this. And so what I'm going to do is I'm going to just state 2 black box results from complex analysis. I hope they seem reasonable. And what they're designed to do is to deal with issues exactly like this. The problem here is that these 2 distributions, they have the same values for integral moments. The 0th, 1st, 2nd, 3rd, 4th. If you do a little bit more work, you can show they have the same half integral moments. The half moment, the 3/2 moment, the 5/2 moment. Okay, we've never really talked about them. It doesn't have the same significance as the mean and the variance. But if I want the 3/2 moment, I just integrate x to the 3/2 times my density. They don't agree for other moments. And so what you really need in complex analysis is if you have 2 functions and their moments agree for all values in an open interval, then they have to be the same. If they only agree on a disconnected set, they may be different. And that's really what's going on, is we need some advanced results from analysis, which we will not get into in this class, but I may get into depending on how the vote goes in complex analysis. All right, so black box results from complex analysis. So we are not going to open up these results and really see what's going on. I think there's better things to do with the end of the semester. But it's nice to just get some sense of why things are true and what do we need to make things rigorous. So the first is, let's say, x and y are random variables. Delta is greater than 0. And the moment generating function of x equals the moment generating function of y for all t less than delta. So I have two random variables. Their generating functions are the same in some neighborhood of the origin. What can we conclude? What do you think we can conclude? If you were in charge of creating calculus, what would the derivative of a product be? Product of the derivatives. Okay? Over here, if you have two functions whose moment generating functions are the same, what would you love to conclude? They're the same. Then the cumulative distribution functions fx and fy are the same. So fx equals fy almost everywhere. So I'm not going to go in too much into what almost everywhere means. I just want to say a few words. If my functions are continuous, if my densities are continuous, then they'll be equal everywhere. The difficulty is if I have the cumulative distribution functions. Remember, the cumulative distribution functions are defined by integrating things. For example, let's let x be 1 if 0 less than equal to x less than equal to 1, 0 otherwise. And let y be 1 if 0 less than equal to x less than equal to 1, and x is not an element of, I would say x, I cannot write it as a over 2 to the n for a an integer, and n less than equal to 2013. Okay? I could do it, of course, for all n, but then I would have an infinite set, and just for the purposes of this example. So is the density of y the density of a uniform random variable? The hint is any answer is fine. I'll accept either yes or no.
No.
No, okay, why is it not the density of a uniform random variable?
Because there are points in the interval 0, 1 for which it's not.
Sure. That's a pretty good reason, right? It doesn't have the same density as the uniform random variable. All right, now does somebody want to argue why it is the density of a uniform random variable? Yes. You seem indecisive today, but go for it.
It has the same cumulative density function.
It has the same cumulative density function. The fact that I've changed it on finitely many points doesn't really change any of the integration I do. I calculate probabilities by integrating over regions. These will give rise to the same probabilities. So if they give rise to the same probabilities, shouldn't I still call this the uniform random variable? Well, then I can't really say the uniform random variable, right? There's no longer a unique definition unless you say two random variables are equal if they only differ on sets that integrate to 0. And this leads to the notion of almost everywhere, which in a measure theory class you would really get your hands into and really get a sense of the nuts and the bolts of the theory. for us, I really don't want to get into that. I just want you to be aware of what there is and what you need to do to make the theory rigorous. Okay, any questions on the first theorem? It's exactly what you would want. Okay? There is an issue with the first theorem, though, that this is not always going to exist. Right? The very first thing you want to do whenever you get any quantity in the world is to ask yourself, does the quantity exist? And so I can give you examples of functions whose moment-generating functions do not exist. And if somebody reminds me, I will give you one on Wednesday. Okay. All right, 2. All right. So we have xi is sequence of random variables, x a random variable, delta greater than 0, for all t such that the absolute value of t is less than delta. Assume the limit as I goes to infinity of the moment generating function of xi at t equals the moment generating function of x at t. Alright, so I have some neighborhood of the origin, and in that neighborhood, for any t, the moment generating function of xi evaluated at t, as I gets very, very large, converges to the moment generating function of x. What would you like to conclude? Your wish list, the holidays are approaching. Festivus is almost upon us. Right? What would you like to conclude?
xi converges to x.
So in some sense, xi converges to x. So xi converges to x. There's lots of different types of convergence. So in particular, the cumulative distribution function of xi converges to the cumulative distribution function of x. Okay? These are wonderful results to have. Unfortunately, we don't always have moment generating functions exist. So on Wednesday, I will give you an example of one that doesn't exist. I suggest you try to think of one between now and then. And I will give you a tweak of the moment generating function that always exists. It's a little bit more complicated, but not that much so. And it has the benefit of always existing. And that's a pretty good, trade-off. Okay? So these are our wish list theorems. Okay? And so, they may or may not be proved in 372 this semester. There's some discussion about these in, I think, the complex analysis appendix of the textbook. And if anybody is interested in more details on this, let me know. If anybody's looking for a project to do for this class, for 10% of your grade, getting the complete proof of the central limit theorem is a great thing to do. It all comes down to the difficulty of, I have some type of convergence of the moment generating functions. I want to somehow go from that to the cumulative distribution functions are converging, or my random variables are converging. The difficulty is inverting the process. Is just because I have this kind of convergence doesn't necessarily mean that the random variables themselves are converging. And so the danger was I gave you 2 random variables that had the same moments, but they were different. If they have the same moments, what can you say about their moment generating functions?
They're the same.
They would be the same. And that would be a big problem. Okay? So we need to avoid stuff like that. If we restrict ourselves to nice random variables, we can often compute these things directly, but then we have to invert the moment generating function at the end. There are techniques to do this. This is really complex analysis, but I want you to at least get a sense of what's going on. Okay. Any questions on what we've done so far? What I thought I would do today, since I'm the professor I can, is prove the central limit theorem for the case of sums of Poisson random variables. But in doing the proof, I want to do the proof as general as possible, as long as possible. And then we'll see that we really don't need the crutch of looking at a Poisson random variable, that the argument really holds in much greater generality. One of the things that's nice about the Poisson random variable is we know exactly what its moment generating function is. And because we know its moment generating function, we can work with it exactly. If we don't know the moment generating function, we have to Taylor expand it and just have some arbitrary parameters. It's not that much more work to do, but it's such an important concept, I want to do it twice. I also want to put a question on this on the exam, where I will give you some nice density and ask you to work on it on the final exam. So you should have no excuse now of being surprised about that problem. Right? There will be a problem on the final where I give you, here's a density, calculate its moment generating function, and directly prove from that. Okay? I am warning you now, I will not accept a proof of the general formula and then just substituting the parameters in at the end of the day. I want you to actually work with the specific generating function I give you. Alright, I want to review, a quick review of standardization. If you see a product, what do?
Take a lot.
Yes. Unless, we put the asterisk in, unless you're talking to, junior high school kids, elementary school kids, for the most part, you see a product, you take the logarithm. If I give you a random variable x, I want to transform it to a new random variable z. And we're going to define z as x minus the expected value of x divided by the standard deviation of x. And so we'll call this standardization. We showed a discussion about this when we were looking at the mean of n random variables on Friday. The advantage of this is this new random variable z has mean 0 and variance 1. So mu of z equals 0, sigma z squared equals 1. And this allows us to compare apples and apples. So we talked about the change of base formula for logarithms. What's so nice about the change of basis formulas for logarithms? Logs, change of base. The log base b of x is the log base c of x over the log base c of b. What's nice about this formula?
You only need to know logs in one base.
Right. So, no logs in one base, no in all. So again, people's job used to be calculating logarithms of numbers. Boring job in my mind. This at least limits what you have to do. All you have to do is get logarithms in one base, and you know logarithms in every base. This is why in most books on probability, if there's a table for the standard for normal distribution, they only give you the table for the standard normal. They count on you to just do the necessary adjustments, the standardization, to make your random variable have mean 0, variance 1, so that that's the normal you need to look at. How many of you have taken statistics and seen like t-distributions? So why do we have to have more tables for t-distributions?
Depends on the degrees of freedom.
Depends on the degrees of freedom. And why do they typically stop after about 29 or 30 degrees of freedom?
Because then, isn't it pretty similar to a normal?
Yeah, it's essentially normal at that point. So typically about 30 is more than enough to have complete knowledge of t-distributions. So for us, we're going to be looking at z or zn is going to be x1 plus xn minus, do you guys want capital N or lowercase n? Minus n times mu. And now, if I calculate the variance of the numerator, I'm going to get n times the variance of each one. So the standard deviation is going to be square root of n times sigma. So I have to divide by sigma square root of n. No, let's make that a capital N. Alright. So now we have a random variable that has mean 0, variance 1, and it's essentially the mean of a sample. So again, I'm trying to estimate some population parameter. Remember, I'm trying to estimate the average value. I'm looking at maybe household income, height, weight, people's likelihood of the Red Sox, predicting the Red Sox will repeat in 2014. Lots of different one. If that's true, email me and I will retroactively add extra credit. Alright? And so how do I get this? I take lots of different independent samples and I add them up. And the central limit theorem basically says the more I add, the tighter this is going to be concentrated about the true population value when I appropriately normalize. Okay? So it's an extremely powerful result. Not only is it giving us what the expected value of this is, but it's telling us how concentrated it is. And the normal decays very rapidly. So as a nice exercise, try to calculate the probability of being 4 standard deviations away from the mean and the normal, or even better, 10 standard deviations. If the probability is so close to 0, we don't even worry about it. Okay. So what we want to do now is we want to prove, modulo the results from complex analysis, which I've just, erased, that sums of Poisson random variables become normally distributed. Have we proved that already in this class? Yes. How do we do it? Stirling. So we used Stirling's formula to show that sums of Poisson random variables converges to a normal. We can do this because we know what the sum of Poisson random variables are. The sum of independent Poissons is Poisson. And then we just use Stirling's formula to expand things. We also did the binomial case, flipping a fair coin. And we were able to do that directly by using Stirling. Okay, what we're going to do now is we're going to stop using Stirling. We're going to prove the central limit theorem directly for Poisson random variables. And in fact, you can then reverse engineer the argument and use this to get Stirling's formula. So if you know the central limit theorem, Stirling's formula is a nice consequence. Okay, so Poisson to CLT. Okay, so let's say each xi is Poisson with parameter lambda. So what is the mean? Does anybody remember the mean? It's lambda. The mean is the easy one because we normally choose our parameters so that the mean is lambda. This is why I don't like the alternate definition for the exponential. The harder one, which I always forget, is what's the variance? I had to look it up. I think it was lambda squared. I think it's just lambda. Yeah, it's just lambda. And sigma squared is lambda. The problem is we can't use dimensional analysis to help us here. Because for the Poisson, lambda is dimensionless. Because we have the probability that xi equals m is lambda to the m e to the minus lambda divided by m factorial. Lambda is unitless. When we did the exponential, lambda was wonderful. Lambda had the same parameters. We could give lambda the length of meters. And so the expectation was lambda. The variance had to be of the form lambda squared. We don't have that fortune here. Alright, anybody remember the moment generating function? Or at least what unique feature it has? Double exponential, right? It was e to the t minus 1 times lambda. And if you start Taylor expanding this, you'll get t plus t squared over 2 plus dot 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 dot. Right? This is a double exponential. And then we had a formula from last time. The moment generating function of ax plus b of t was equal to, I think, e to the bt, moment generating function of x at at. And just to quickly reprove that, I will just, the moment generating function of ax plus b of t is the expected value of e to the ax plus b times t. We can pull out the e to the bt because that has no x dependence, and we get the expected value of e to the ax with a t, and then that is just the moment generating function of x evaluated at a times t. I will admit I never remember this formula. I have to just quickly rederive it. But if you remember the definition of the moment generating function, it's the expected value of e to the tx. You can figure this out without too much trouble. There's one other fact about moment generating functions we have that's extremely important. And we haven't really used it that much yet. But we're going to be using it non-stop from this point onward. What nice fact does the moment generating function have? And somehow it's got to be related to something that's going to be coming in here. So that's one, but I have here something involving sums of random variables. So what's the formula I have that involves sums?
Linearity of expectation.
So linearity of expectation basically comes in, and that gives us the moment generating function of a sum is the,
So it's the moment generating function.
can't be the sum, product. Because remember, we're exponentiating everything. So linearity in the exponential becomes a product. And so the big fact for us is that the sum is, the moment generating function of the sum is the product of the moment generating functions. So now let's study the moment generating function of Zn of t. This is going to be the moment generating function. This is all in the book. So if you want to just sit back and kind of let the algebra flow, by all means feel free to do so. There's not going to be too much different than just rolling up our sleeves and going through it. We've got x1 plus xn minus n mu over sigma root n of t. So the first thing I'm going to do is use the fact that if I take the plus b, it's e to the bt times the rest. So what does my b equal? Right. And so one of the n's cancels, or one of the square roots of n's cancel, and I get e to the negative mu root n divided by sigma. And actually there's a t up top, right? And now I have the moment generating function of x1 over sigma root n plus dot 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 plus xn over sigma root n of t. I just want to do this very slowly. I don't want to skip steps. Now I use the moment generating function of a sum of random variables is the product of the moment generating functions. So I will get e to the negative u square root of n t over sigma. Then product I equals 1 to n, the moment generating function of xi over sigma root n of t. Okay, now what do I use? Yes, but not right now. So put that in the bank. Why are you saying logs? Yeah, or this is Professor Miller's class. Either one of those is acceptable. Right? There's a product in here. We should be thinking of logs at some point. But I want to do one more simplification before I invoke the logs. Which thing about moment generating function should I use? Yes.
It's
Right. And
so to get rid of the fraction.
get rid of the fraction. This is really 1 over sigma root n xi. So really I have a equals 1 over sigma root n. So I can use that result and get e to the negative mu square root of n t over sigma product I equals 1 to n of m xi of t over sigma root n. Now there's something really nice about this. Most of the time what you want to do and what you are asked to do in mathematics are not even close to being the same. Right? If you had to evaluate a moment generating function and you could choose where to evaluate the moment generating function, where would you choose? 0. As n gets very, very large, where are we evaluating these moment generating functions? Essentially at 0. Right? That's why things are so nice. Now the difficulty is, if we were to evaluate it exactly at 0, what would we get? 1. So if we were to just say, oh, screw this, this is essentially just evaluating it at 0, this is false, okay? So we'll write false here. Then this is just e to the negative mu square root of n t over sigma times 1 to the n. So that would basically be telling us strange things. There would be really no dependence at all on the distribution, unless maybe somehow in our approximation of, what does, the error term for this equal. And then the question is, of course, what function has this as its moment generating function? So what we can do, however, is we can say, well, look, our variables are independent, identically distributed. So this is the same as e to the minus mu square root of n t over sigma times the moment generating function, let's call it of x, at t over sigma square root of n to the nth power. So m zn of t. So we're going to box this off. Okay? Horrible box, but this is a great formula. So far, have I used any special properties of the random variables xi? No, all I've used is independent, identically distributed. I have not used that it's a Poisson. Getting up to this point is the same for every random variable. What do I want to show that this whole thing converges to?
Normal.
A normal. Which normal?
Standard.
The standard normal. Alright, so this part of the argument now is, let's calculate what is the moment generating function of the standard normal. You can, of course, do the moment generating function of any normal. And in fact, if you know the moment generating function of the standard normal, by doing the change of variable, the thing I just erased sadly, the ax plus b, you can then get the moment generating function of any normal. I will only do the moment generating function of the standard normal for what reason?
Easier.
It's easier.
So the one we would need. Right
It's the
now.
only one we need, right? I do not care so much about calculating moment generating functions that I will calculate that of an arbitrary normal. We don't need that. So let's let z be normal 0, 1. What is the moment generating function of z? So we typically use z for normal. Some letter had to be taken. This is one of the reasons why I'm calling the other variable z sub n, to show us I'm converging to that. Alright, so the moment generating function of z is going to be the expected value of e to the tz. That's going to be the integral from minus infinity to infinity, e to the tz, 1 over square root of 2 pi, e to the negative z squared over 2 dz. I apologize for the potential confusion between z's and 2's. Okay. If t equals 0, that's just the integral of the standard normal. We know how to do that. And in fact, we know how to integrate any normal. How should we evaluate this integral? Does this relate to anything we know? Alright, so this is the opposite of my... I don't want to discriminate. I want to be inclusive today. What should we do? What kind of algebraic simplification should we do? calculus argument. Algebraic.
Put the powers of E together.
Put the powers of E together, right? We're being inclusive today, right? Right, they're together. Look, I've got an E to the TZ. How many of you have seen Ghostbusters? Probably the greatest comedy of all time. Okay? Towards the end of the movie, when they've captured the Keymaster, and Venkman is over at the Gatekeeper, or maybe I've got them mixed up, and your Egon is describing what's going on, and Venkman says, we have to get these two together. Right? Okay, in Ghostbusters, it's catastrophic. But here, we want to get these two together. I've got an exponential, I've got an exponential. Well, why don't we get together and exponentiate, right? What happens? 1 over square root of 2 pi, integral minus infinity to infinity, e to the negative z squared minus 2tz over 2 dz. I'm just writing the algebra in a little bit of a nice way because I know the punchline. And if you actually give me any quote in Ghostbusters, I will give you the next line of Ghostbusters as well. Okay? Why am I writing it like this? What is this looking like? Yes?
A function that we can factor,
Okay.
which is some distribution.
You're going to go all the way back to like 7th or 8th grade.
Or complete the square.
Complete the square. Right? Minus infinity to infinity, e to the negative, so I have a z squared minus 2tz, so I want to add a t squared, right? So this becomes a z minus t squared. I add a t squared, so I'm going to have a, let me do this slowly or I will make a mistake. Minus 2tz plus t squared minus t squared over 2 dz. I'm sorry? Ah, yes, thank you, z squared. So now notice this minus t squared has a minus in front of it, so when I pull it outside the integral, I'll get an e to the t squared over 2. So the e to the t squared over 2, 1 over, and I'm going to bring the square root of 2 pi back inside, minus infinity to infinity, 1 over square root of 2 pi, e to the negative, let's see, z minus t squared over 2 dz. What does that integral equal? Yes?
The normal of mean t.
Normal of mean t. So what does it equal? So you're integrating a probability distribution function. What do you get? 1. Right? If I'm asking you, without having you, doing the integration, it's got to either be 1, 0, something nice like that. One of the big facts is, if I can ever work the algebra, so I'm integrating something that's a probability distribution, I know it's just 1. So I get e to the t squared over 2 times 1, which is better known as e to the t squared over 2. So now we know the moment generating function of the standard normal. It's e to the t squared over 2. So this nightmarish identity we have over here should be converging to e to the t squared over 2. At least if t is sufficiently close to the origin. Well, in fact, we're evaluating things at t over sigma root n. So, alright. A lot of algebra so far. Any questions what we've done here? So again, whenever you see the exponentials like this, it's natural to try to combine them and see, well, maybe I start off with one normal distribution and I end up with a related normal distribution which I understand and can work with. So this is a really good algebra idea. Completing the square, it's for more than just solving the quadratic formula. Okay? So it's a really good technique to have. It's going to be a battle with the clock to see if we make it in time. This is a lecture where you do not want to stop halfway through or 80% through. Right? It's a pain to have to set everything up again. So we'll remember there was lambda and lambda for both of them. So we have mzn of t was e to the negative mu square root of n t over sigma times mx of t over sigma root n to the n, and mx of t was e to the t minus 1 lambda. All right, now I will return. What should I do? Now I take logs. Now can you figure out why I have chosen of all random variables to study for this specific calculation, why I chose to study the Poisson?
You have e raised to a
I
power.
have e raised to something. If I'm going to take logs of it, not only can I take logs easily, it makes things even nicer. Right? It's not a coincidence that this is the one I chose. So now if I look at the log of m zn of t, I get negative mu square root of n t over sigma plus n log mx t over sigma square root of n. And so we'll save this result for tomorrow. Right? Now we'll plug in what we actually know. So we get the log of m zn of t. Mu was just lambda. So we get negative lambda square root of n t. And what was sigma? Square root of lambda. Let's hope everything works out. Plus n times the log of this. We get, very carefully, e to the t over square root of lambda square root of n minus 1 times lambda. And the reason is, remember, we're evaluating mx not at t, but at t over sigma root n. And t over sigma square root of n is t over square root of lambda square root of n. Okay? If the moment generating function of the normal is e to the t squared over 2, what should its logarithm look like? So I want to show that this equals t squared over 2. Alright, so let's see what happens. Lambda divided by square root of lambda is square root of lambda. So we get negative square root of lambda square root of n t. Okay, this is what's known as bad. Right? As n gets very, very large, what happens to this term? It gets large. So we need this to be cancelled with something from over here. Okay?
Shouldn't one of us be a lambda?
Yes, one of them should be a lambda. I think this one, though. I don't think it really matters too much. Alright, now over here we have plus n times the following. Oh, good. So the n is huge. So that can magnify things here. So we want the Taylor series expansion of e to the blah minus 1. So when we expand e, we get 1 plus, okay, the 1 cancels. Then we'll get this to the first power. So we get t over square root of lambda square root of n. The next term is going to be t squared over lambda n with a 2 plus t cubed over 6 lambda to the 3 halves n to the 3 halves plus dot 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 times lambda. Alright. Does the series converge for fixed value of t? Yes. Right? The exponential always converges, and to make matters even better, I'm dividing by square roots of n to higher and higher powers. So I have terrific convergence. I have convergence from factorials, I have convergence from square roots of n. The first piece, t square root of lambda, and lambda becomes the square root of lambda upstairs, n and square root of n downstairs becomes square root of n, that precisely cancels that piece. Next piece, lambda cancels, n cancels, I get t squared over 2. Alright, things are looking really good. The next piece is going to be t cubed. Now I've got a 6, I'll call it 3 factorial, square root of lambda, and then I have n times n to the 3 halves, I have square root of n. Plus the next piece would be t to the fourth over 4 factorial. I would have a lambda squared, lambda over lambda, lambda and a lambda squared would give me a lambda, and then I'd have an n, I would have an n squared, I would have an n down below. I get higher and higher and higher powers of n. So what's going to happen as n goes to infinity? All the other terms go to infinity. So as n goes to infinity, the log of the moment generating function of Zn of t converges to t squared over 2. Well, if the log is converging to that, what's the moment generating function converging to? E to the t squared over 2. Which is the moment generating function of a random variable with mean 0 variance 1 that's normally distributed. That's exactly what we wanted to show. And we even have about 3 minutes to just, let this sink in. Right? The difficulty is to show that just because the moment generating functions are converging, the random variables themselves actually converge. How crucial in our argument was it that we had a Poisson random variable? Where did we use that? Was this just for convenience, or did we crucially use this in our argument? Yes, we replaced mx with this. But then, once we had this, what do we immediately do? So really, all we need is the Taylor series expansion of the log of the moment generating function. Well, if I know the moment generating function, I can calculate the logarithm, I can calculate the Taylor series expansion. Maybe I can just more generally calculate the log of the Taylor series. That's going to just be a little bit more work, a little bit more algebra. It'd be nice to have 3 blackboards for that, but we should be able to hopefully squeeze it into 2. We do have those, but those, I will combine exponentials and put them together, but combining blackboards here and there, that's just wrong. Yeah, I mean that one's like the Monty Python, that's the 5. Like 1, 2, 3, 4, 5. That one's right out. So we won't use that blackboard. Right? Unless we have the class change the seating preferences. So, okay, so to recap, we've got the convergence. We use the black box result from complex analysis and now say it's normally distributed. We actually have more. Not only do we have convergence, but we have an estimate of how far away it is from the moment generating function of the standard normal. Okay, we have to exponentiate things, but the main term is controlled by this. And it turns out, if you do a little bit more algebra and a little bit more grouping as to what is going on, this is essentially related to the third moment of your random variable. And the third moment is what controls the speed of convergence. If you think about it, something like this is reasonable. If I give you a random variable, I can always adjust it to have mean 0, if it has finite mean. So the mean can't really provide me any good information. I can always rescale to have it have, standard deviation 1. So the second moment can't really provide me any information. So does every random variable look like every other random variable? No. Differences should come into play. And the differences start to come into play with the third moment. If you have a distribution that's symmetric about the origin, what will the third moment be? 0. So then the fourth moment would come into play. And if you think back to your calculus tests for maxima and minima, what happens unfortunately if the second derivative vanishes and you have to go into the third derivative, it's the same thing here. If the third moment vanishes, you move on to the fourth moment. Could the fourth moment be 0? Think carefully before you answer. Can the fourth moment of a random variable be 0?
No.
No.
Wait, why did you say?
Can the fourth moment of a random variable, can the integral of x to the fourth p of x dx be 0? Or the sum of, xn to the fourth f of xn be 0?
No.
Try again.
Yes.
Yes. There's one random variable that has 0 fourth moment. Yes, a random variable that's 0 everywhere. Right? The only random variable that is 0 everywhere, the only random variable that has 0th fourth moment is 0 everywhere. Right? We're really not going to try to use the central limit theorem to understand what's going on in that case. I don't know if I would call it a variable. I'd call it a constant. Right? So staying away from situations like that, the third and the fourth moments will tell you how fast the convergence is happening. Alright, so there's going to be no written homework this week. What I want you to do is use this week to reassess where you are in the class. Look at the exam, look at the previous material, read the stuff on the central limit theorem, and then talk to me about how you're doing if you want to, so we have a good game plan going into the final. Right? You've worked hard for the semester.